Today we're going to be doing prerequisite lesson 6. Prerequisite lesson 6 is related to using trig functions to simplify trig expressions, and then we'll be moving into simplifying proving identities. Lesson 7 will be solving trig equations. So as a little bit of background at the top of these notes, we know that this is the unit circle, and we know that because it's centered at 0, 0. So this would be located at the origin. We know that the radius of the unit circle is equal to 1. Right. On the unit circle itself, we have learned that if we draw in our right triangle, okay, so let's also assume here that this is going to be the 45 in quadrant 1. So that's going to give me a root 2 over 2 and a root 2 over 2 unit circle value. This is my x and this is my y. We discovered that when we do this is our theta and we say the adjacent over the hypotenuse, root 2 over 2 over 1, which is cosine, we can simplify and just say that the cosine value is going to be the x value of the ordered pair, and the sine of theta is going to be the y value. Now, as we move into trig terms and trig equations, theta is going to actually be replaced with, and this can be confusing, the variable x. So basically what I'm saying is that this in here becomes an x, but this is not x as in x of the coordinate x comma y. This is x as in the size of the angle, whether that be in degrees or in radians. Okay, so something to keep in mind here is that I could ask you, which was yesterday's work, the cosine at pi over 4, and we would say that the cosine of pi over 4 would be the x value, which is root 2 over 2, or the sine of pi over 4. Notice how x was replaced with the radian value, and again, I'm going to get root 2 over 2. So as you can see here, when I ask the question, what does the x mean in sine of x, what it means is that that's going to be my either radians or degrees for a given location on the unit circle. Okay, but the sine of x means I want the y value at the angle that represents x. Okay, so here's what we know. X can be either degrees or radians. Traditionally, we use theta when we want the answer in degrees, or we will use x when we want radians, or we could use the variable t. Now, a new thing for you is going to be, what about cosine squared x? Cosine squared x is the notation for cosine x times cosine x. Okay? Anytime we take two trig functions times themselves, we write it as cosine squared x. What we do not write is the cosine of x squared, because x squared would be, think about it, if that was 100 degrees, 100 squared would be 10,000. That's not what we're doing. We're talking about taking the actual x value of an ordered pair and multiplying it times itself. So this would be like root 2 over 2 times root 2 over 2. All right. When we don't know what x is, we need to remember that this is the relationship that cosine squared x signifies. Okay, so these are not the same thing. This is not correct. This is correct. Now, in our basic identities, I'm going to give you a list of them, of things that we work with, and then we'll come back and talk about some of them. So sine of x could also be redefined as 1 over cosecant x. This could be 1 over secant x, 1 over cotangent x, 1 over tangent x. Secant is 1 over cosine x, we know that already, and cosecant is 1 over sine x. Okay, now just to explain this real carefully to you, let's take a look at just this one here and just do one subset explanation of that. So if we think back, we know that sine is the y value of the ordered pair. Okay, set equal to 1 over the cosecant, and we know from the last section that cosecant is 1 over y. Notice the rule when I take 1 over y and I multiply by its reciprocal. Doesn't that give me 1 times y over 1, which is the definition of y? That's where these come from, manipulating these fractions. All right, for now I'm going to give them to you as straight definitions to be used. In the quotient identities, we'll use these a lot. If you remember, tangent was y over x on the unit circle. Y is the sine of x is the cosine of x. Cotangent is x over y, so this is cosine x over the sine of x. All right? These are our basic players in order to simplify problems. So now, as you can see in the bottom, the first two examples, we can use algebra to manipulate these trigonometric terms. It often involves substitution and simplification, factoring using GCF, and binomial techniques and fractions. So here's our introductory examples. Level A, basic problems. They're asked to simplify cotangent x times secant x. One good practice is to always go back to sines and cosines. You may not want to do that on every problem, and you'll see that, but that is one introductory strategy. So cotangent is cosine x over sine x. So I'm substituting. Secant x is 1 over cosine x. As you can see, when I multiply two fractions, I can cancel, which leaves me with 1 over sine x. Now I understand that looks pretty simple to you, but 1 over sine x up here is defined as cosecant x. So what that means is that I could take the product of these two answers, and it should equal the same thing as just whatever the cosecant of the angle originally was. When I look at example 2, and I'm given something where I have a term out front times a quantity, this is an example where maybe I want to distribute and then simplify. So notice I've changed Greek symbols. I don't have x, I don't have theta, I have a different Greek symbol. It's treated exactly the same. So it's sine times cosecant minus, now remember, sine times sine, we learned this earlier in the notes, is sine squared. When I come into here, sine can stay, cosecant is 1 over sine. This I can put over 1, cancels. Anytime everything cancels, it leaves me with 1 minus sine squared. Now, I'm going to highlight this because this is an example of what we call a Pythagorean identity. So what I'm going to do now is I'm going to go introduce the first Pythagorean identity and then come back to this problem here. So if I look at my next page of notes, I have these Pythagorean identities that are here. Okay, I know it looks the same. We will manipulate the last two in a few minutes. But this is cosine squared plus sine squared equals 1. And I just want to show you on this one, if I have a quadrant 1 point, and this is a unit circle value. This is x, this is y, this is 1. According to the Pythagorean theorem that we use with right triangles, don't we get x squared plus y squared equals 1? That would be a valid, actually 1 squared Pythagorean theorem application. So now we're just going to replace x squared with cosine squared x and y squared with sine squared x. This is my reasoning for where this Pythagorean identity actually comes from. Now, this is a true identities are true. What's on the left is equal to what's on the right. However, we can also move these around. So if I take cosine squared x and say 1 minus sine squared x, these two things are the same thing. Okay, take a look at this, 1 minus sine squared x. And then let's go back to the example I have here. Notice I have 1 minus sine squared with a different Greek symbol. I can substitute using this Pythagorean identity and say that this is the same thing as just cosine squared because I manipulated using legal algebra and then I substituted. So this is actually the answer that I would be looking for the second problem. All right, let's move on. 2 more examples. So my next example is going to result in a very complex fraction. Cosine squared x times sine cubed x. All right. Now, if we look at this, I should be able to cancel this sign with one of the ones in the bottom. When I cancel the ones in the bottom, it's going to leave me with sine squared x. Remember, I had 3 multiplications in the bottom. Now I only have 2. That leaves me with cosine squared x over sine squared x. Okay? This could be rewritten as cosine x times cosine x over sine x times sine x. According to our quotient identities, cosine over sine is the same thing as cotangent. So this then would be cotangent x times cotangent x, which results in cotangent squared x as my final solution. So these became transformed into something smaller, and then notice how I wrote my final answer. In my next example, where I have 2 fractions being added together, this is an example of what we're going to call an LCD. All right? My LCD is going to be 1 minus cosine x and 1 plus cosine x. Okay? Now, these do not involve Pythagorean identities. Okay? And let me just quickly refer back to those for a moment. So if I go back to my original Pythagorean identity, do you notice that I do not have just cosine and sine? They have to be squared. These are not squared at this time. So these will not involve Pythagorean identity. But I can go ahead and do LCD, which is these 2 quantities multiplied times each other. 2 over 1 minus cosine x plus 2 over 1 plus cosine x. What I'm missing here is going to be the 1 plus cosine x. I need that here. So I'm going to multiply this times 1 plus cosine x over 1 plus cosine x. Now, if you don't remember rationals, rationals are important because we need to multiply by what we're missing, top and bottom, which change the form, but not the value. This one's going to be multiplied by 1 minus cosine x. Up top, I can distribute here and here. I'm going to leave my denominator in factored form for right now. When I distribute up top, I get a 2 plus 2 cosine x plus 2 minus 2 cosine x. Okay, combining like terms, so now we're going to do combine like terms. These are going to cancel here and here, which leaves me with 4 over, and now we could FOIL this out. So when we FOIL this, we're going to get 1 plus cosine x minus cosine x minus cosine squared x. 1 minus cosine squared x. And guess what we have with 1 minus cosine squared x? Our favorite Pythagorean identity. So if you look down below, let me push this up here a second. This was the readjustment of the original Pythagorean identity where we isolated cosine. Now I could also take, and I could turn this into sine squared x is equal to 1 minus cosine squared x. So now in my problem here, I get 4 over sine squared x. I'm going to rewrite this as 4 times 1 over sine squared x. Remember, this could be written twice, 1 over sine x, 1 over sine x, which if you look back on your original notes, 1 over sine is cosecant. So this is the same thing as 4 cosecant squared x. Okay, so remember, 1 over sine is equal to cosecant. There's my substitution. Now, as we move into more Pythagorean identities, okay, they can all be derived from the original cosine squared plus sine squared. Okay, so this is our major, number 1. If I take each one of these and divide by cosine squared x, I can rewrite this. Cosine squared over cosine squared is 1, plus sine squared over cosine squared is tangent squared. 1 over cosine squared is secant squared. This is my second Pythagorean identity. Now I can take all of these and multiply by sine squared x. not multiply rather, divide. Cosine over sine is cotangent. What I've boxed in are my three major Pythagorean identities that I can manipulate, isolate terms, and substitute as needed to make problems smaller, which we've seen in previous examples. So let's do some problems down here at the bottom. These are Pythagorean examples. So when I'm given this, what I should notice is this is one term times another plus a term. Okay? Now it doesn't say to do this, but my algebra strategy is going to be GCF. What is common to both of these is secant squared x. When I GCF this, take out the secant squared, I'm left with tangent squared. Take out the secant squared, I'm left with 1. Tangent squared plus 1, if I come back up here, is the same thing as secant squared. So this is the Pythagorean identity substitution, turning that into secant squared x times the secant squared x on the outside is going to be secant to the 4th x. In B6, this is going to be what your teachers call FOIL, or double distributing. So I'm going to take secant times secant. I'm going to get secant squared x plus secant x tangent x minus tangent x secant x minus tangent squared x. The middle terms will cancel. Remember, negative AB plus BA cancels. You can change the order when you're multiplying. So that leaves me with secant squared x minus tangent squared x. If I check this out up here and I rearrange it, secant squared x minus tangent squared x equals 1. So that is my solution, just 1. Our last problem for the day is a higher order than quadratic, but it's going to mirror quadratic factoring. Okay, so if I rewrite this problem as cosine to the 4th x minus 2 cosine squared x plus 1, I'm going to take out the trig terms right above so you can see this. C to the 4th minus 2c squared plus 1. Okay, my factoring for this is the binomial technique, where I'm going to say cosine squared x and cosine squared x. If you multiply these two, it's going to give you cosine to the 4th. And now, what two numbers multiply to give me 1, but add to give me negative 2? In this case, they're both minus 1s. Now, what we need to see here is that cosine squared minus 1 and cosine squared minus 1 are each, as separate quantities, examples of a Pythagorean identity. So if I go back up to the top, I could rearrange this to say cosine squared x minus 1 is equal to negative sine squared x. Be careful when you're moving things left and right. You've got to watch your signs. So notice when the 1 came to the left, it became minus, and when the sine squared moved to the right, it became minus. So my substitution down at the bottom is now going to be negative sine squared x times negative sine squared x, where I replace the purple with its shorter Pythagorean identity side. Negative times a negative is positive sine to the 4th x. In your notes, you can go ahead and pause the video and fill these in. This is the sheet, just like a Post-it that we used when we were graphing lines, that has all the basic key identities. You will use sine x, you will use cosine x. You will use the quotient identities, going back to sines and cosines. Cosecant and secant most likely will be put back into the cosine and sine formats, and here are your basic Pythagorean identities that you'll have to manipulate. The assignment today is much easier than the problems in the notes. Tomorrow we will do another assignment similar to the problems we did in the notes.